In the branch of mathematics known as real analysis, the Riemann integral, created by Bernhard Riemann, was the first rigorous definition of the integral of a function on an interval. For many functions and practical applications, the Riemann integral can be evaluated by the fundamental theorem of calculus or approximated by numerical integration. The Riemann integral is unsuitable for many theoretical purposes. Some of the technical deficiencies in Riemann integration can be remedied with the Riemann-Stieltjes integral, and most disappear with the Lebesgue integral. Overview: let f be a non-negative real-valued function of the interval, a, b, and let be the region of the plane under the graph of the function f and above the interval, a, b. We are interested in measuring the area of S. Once we have measured it, we will denote the area by. The basic idea of the Riemann integral is to use very simple approximations for the area of S. By taking better and better approximations, we can say that in the limit we get exactly the area of S under the curve. Note that where f can be both positive and negative, the definition of S is modified so that the integral corresponds to the signed area under the graph of f, that is, the area above the x-axis minus the area below the x-axis. Definition: partitions of an interval. A partition of an interval, a, b, is a finite sequence of numbers of the form. Each is called a subinterval of the partition. The mesh or norm of a partition is defined to be the length of the longest subinterval, that is. A tagged partition of an interval, a, b, is a partition together with a finite sequence of numbers subject to the conditions that for each I. In other words, it is a partition together with a distinguished point of every subinterval. The mesh of a tagged partition is the same as that of an ordinary partition. Suppose that two partitions and are both partitions of the interval, a, b. We say that is a refinement of if for each integer I, with, there exists an integer such that and such that for some j with. Said more simply, a refinement of a tagged partition adds tags to the partition, thus it refines the accuracy of the partition. We can define a partial order on the set of all tagged partitions by saying that one tagged partition is greater or equal to another if the former is a refinement of the latter. Riemann sums: choose a real-valued function f which is defined on the interval, a, b. The Riemann sum of f with respect to the tagged partition together with is. Each term in the sum is the product of the value of the function at a given point, and the length of an interval. Consequently, each term represents the area of a rectangle with height and width. The Riemann sum is the signed area under all the rectangles. Riemann integral: loosely speaking, the Riemann integral is the limit of the Riemann sums of a function as the partitions get finer. If the limit exists, then the function is said to be integrable. The Riemann sum can be made as close as desired to the Riemann integral by making the partition fine enough. One important requirement is that the mesh of the partitions must become smaller and smaller, so that in the limit, it is zero. If this were not so, then we would not be getting a good approximation to the function on certain subintervals. In fact, this is enough to define an integral. To be specific, we say that the Riemann integral of f equals S if the following condition holds. For all I micron 0, there exists I such that for any tagged partition and whose mesh is less than I, we have. Unfortunately, this definition is very difficult to use. It would help to develop an equivalent definition of the Riemann integral which is easier to work with. We develop this definition now, with a proof of equivalence following. Our new definition says that the Riemann integral of f equals S if the following condition holds. For all I micron 0, there exists a tagged partition and such that for any tagged partition and which is a refinement of and, we have. Both of these mean that eventually, the Riemann sum of f with respect to any partition gets trapped close to S. Since this is true no matter how close we demand the sums be trapped, we say that the Riemann sums converge to S. These definitions are actually a special case of a more general concept, a net. As we stated earlier, these two definitions are equivalent. In other words, S works in the first definition if and only if S works in the second definition. To show that the first definition implies the second, start with an I micron, and choose AI that satisfies the condition. choose any tagged partition whose mesh is less than I. Its Riemann sum is within I micron of S, and any refinement of this partition will also have mesh less than I, so the Riemann sum of the refinement will also be within I micron of S. To show that the second definition implies the first, it is easiest to use the double integral. First one shows that the second definition is equivalent to the definition of the double integral. For this see the article on double integration. Now E will show that a double integrable function satisfies the first definition. Fix I micron, and choose a partition such that the lower and upper double sums with respect to this partition are within of the value S of the double integral. Let if R equals 0, then f is the zero function, which is clearly both double and Riemann integrable with integral 0. Therefore we will assume that a greater than 0. If m greater than 1, then we choose I such that if m equals 1, then we choose I to be less than 1. Choose a tagged partition and we must show that the Riemann sum is within I micron of S. To see this, choose an interval. If this interval is contained within sum, then where mj and mj are respectively, the infimum and the supremum of f on. If all intervals have this property, then this would conclude the proof, because each term in the Riemann sum would be bounded a corresponding term in the double sums, and we chose the double sums to be near S. This is the case when m equals 1, so the proof is finished in that case. Therefore, we may assume that m greater than 1. In this case, it is possible that one of the is not contained in any. Instead, it may stretch across two of the intervals determined by. In symbols, it may happen that we may assume that all the inequalities are strict because otherwise we are in the previous case by our assumption on the length of I. This can happen at most ∑1 times. To handle this case, we will estimate the difference between the Riemann sum and the double sum by subdividing the partition at. The term in the Riemann sum splits into two terms. Suppose that then. So this term is bounded by the corresponding term in the double sum for each. To bound the other term, notice that it follows. Since this happens at most ∑1 times, the total of all the terms which are not bounded by the double sum is at most A. Therefore the distance between the Riemann sum and S is at most I micron. Examples, let be the function which takes the value 1 at every point. Any Riemann sum of f on 0, 1, will have the value 1, therefore the Riemann integral of f on 0, 1, is 1. Let be the indicator function of the rational numbers in 0, 1. That is, IQ takes the value 1 on rational numbers and 0 on irrational numbers. This function does not have a Riemann integral. To prove this, we will show how to construct tagged partitions whose Riemann sums get arbitrarily close to both 0 and 1. To start, let n be a tagged partition. Choose I micron 0. The t have already been chosen, and we can't change the value of f at those points. But if we cut the partition into tiny pieces around each t, we can minimize the effect of the t. Then, by carefully choosing the new tags, we can make the value of the Riemann sum turn out to be within I micron of either 0 or O near our choice. Our first step is to cut up the partition. There are n of the t, and we want their total effect to be less than I micron. If we confine each of them to an interval of length less than, then the contribution of each t to the Riemann sum will be at least and at most. This makes the total sum at least 0 and at most I micron. So let I be a positive number less than. If it happens that two of the t are within I of each other, choose I smaller. If it happens that some t is within I of some xj, and t is not equal to xj, choose I smaller. Since there are only finitely many t and xj, we can always choose I sufficiently small. Now we add two cuts to the partition for each t. One of the cuts will be at, and the other will be at. If one of these leaves the interval, 0, 1, then we leave it up t will be the tag corresponding to the subinterval. If t is directly on top of one of the xj, then we let t be the tag for both intervals. We still have to choose tags for the other subintervals. We will choose them in two different ways. The first way is to always choose a rational point, so that the Riemann sum is as large as possible. This will make the value of the Riemann sum at least 1 AI micron. The second way is to always choose an irrational point, so that the Riemann sum is as small as possible. This will make the value of the Riemann sum at most I micron. Since we started from an arbitrary partition and ended up as close as we wanted to either 0 or 1, it is false to say that we are eventually trapped near some number s, so this function is not Riemann integrable. However, it is Lebesgue integrable. In the Lebesgue sense its integral is 0, since the function is 0 almost everywhere. But this is a fact that is beyond the reach of the Riemann integral. There are even worse examples. IQ is equivalent to a Riemann integrable function, but there are non-Riemann integrable bounded functions which are not equivalent to any Riemann integrable function. For example, let C be the Smythe Volterra Cantor set, and let IC be its indicator function. Because C is not Jordan measurable, IC is not Riemann integrable. Moreover, no function G equivalent to IC is Riemann integrable. G, like IC, must be 0 on a dense set, so as in the previous example, any Riemann sum of G has a refinement which is within I micron of 0 for any positive number I micron. But if the Riemann integral of G exists, then it must equal the Lebesgue integral of IC, which is 1/2. Therefore G is not Riemann integrable. Similar concepts, it is popular to define the Riemann integral as the Dubut integral. This is because the Dubut integral is technically simpler and because a function is Riemann integrable if and only if it is Dubut integrable. Some calculus books do not use general tagged partitions, but limit themselves to specific types of tagged partitions. If the type of partition is limited too much, some non-integrable functions may appear to be integrable. One popular restriction is the use of left-hand and right-hand Riemann sums. In a left-hand Riemann sum, for all I, and in a right-hand Riemann sum, for all I. Alone this restriction does not impose a problem. We can refine any partition in a way that makes it a left-hand or right-hand sum by subdividing it at each t. In more formal language, the set of all left-hand Riemann sums and the set of all right-hand Riemann sums is cofinal in the set of all tagged partitions. Another popular restriction is the use of regular subdivisions of an interval. For example, the th regular subdivision of 0, 1, consists of the intervals. Again, alone this restriction does not impose a problem, but the reasoning required to see this fact is more difficult than in the case of left-hand and right-hand Riemann sums. However, combining these restrictions, so that one uses only left-hand or right-hand Riemann sums on regularly divided intervals, is dangerous. If a function is known in advance to be Riemann integrable, then this technique will give the correct value of the integral. But under these conditions the indicator function IQ will appear to be integrable on 0, 1, with integral equal to 1, every endpoint of every subinterval will be a rational number, so the function will always be evaluated at rational numbers, and hence it will appear to always equal 1. The problem with this definition becomes apparent when we try to split the integral into two pieces. The following equation ought to hold. If we use regular subdivisions and left-hand or right-hand Riemann sums, then the two terms on the left are equal to 0, since every endpoint except 0 and 1 will be irrational, but as we have seen the term on the right will equal 1. As defined above, the Riemann integral avoids this problem by refusing to integrate IQ. The Lebesgue integral is defined in such a way that all these integrals are 0. Properties, linearity, the Riemann integral is a linear transformation. That is, if f and g are Riemann integrable on a, b, and I plus or minus and I squared are constants, then, because the Riemann integral of a function is a number, this makes the Riemann integral a linear functional on the vector space of Riemann integrable functions. Integrability, a function on a compact interval, a, b, is Riemann integrable if and only if it is bounded and continuous almost everywhere. This is known as the Lebesgue's integrability condition or Lebesgue's criterion for Riemann integrability or the Riemann-Lebesgue theorem. The criterion has nothing to do with the Lebesgue integral. It is due to Lebesgue and uses his measure 0, but makes use of neither Lebesgue's general measure or integral. The integrability condition can be proven in various ways, one of which is sketched below. In particular, a countable set has Lebesgue measure 0, and thus a bounded function with only finitely or countably many discontinuities is Riemann integrable. An indicator function of a bounded set is Riemann integrable if and only if the set is Jordan measurable. If a real-valued function is monotone on the interval, b, it is Riemann integrable, since its set of discontinuities is countable, and therefore of Lebesgue measure 0. If a real-valued function on b is Riemann integrable, it is Lebesgue integrable. That is, Riemann integrability is a stronger condition than Lebesgue integrability. If is a uniformly convergent sequence on b with limit f, then Riemann integrability of all implies Riemann integrability of f, and. However, the Lebesgue monotone convergence theorem does not hold. Generalizations: it is easy to extend the Riemann integral to functions with values in the Euclidean vector space Rn for any n. The integral is defined by linearity. In other words, if f equals then. In particular, since the complex numbers are a real vector space, this allows the integration of complex-valued functions. The Riemann integral is only defined on bounded intervals, and it does not extend well to unbounded intervals. The simplest possible extension is to define such an integral as a limit, in other words, as an improper integral. This definition carries with it some subtleties, such as the fact that it is not always equivalent to compute. For example, consider the function f, x, which is 0 at x equals 0, 1 for x greater than 0, and a 1 for x less than 0. By symmetry, always, regardless of a. But there are many ways for the interval of integration to expand to fill the real line, and other ways can produce different results. In other words, the multivariate limit does not always exist. Computing yields a, and computing yields a. In general, this improper Riemann integral is undefined. Even standardizing a way for the interval to approach the real line does not work because it leads to disturbingly counterintuitive results. If we agree that the improper integral should always be, then the integral of the translation f, xa1, is a 2, so this definition is not invariant under shifts, a highly undesirable property. In fact, not only does this function not have an improper Riemann integral, its Lebesgue integral is also undefined. Unfortunately, the improper Riemann integral is not powerful enough. The most severe problem is that there are no widely applicable theorems for commuting improper Riemann integrals with limits of functions. In applications such as Fourier series, it is important to be able to approximate the integral of a function using integrals of approximations to the function. For proper Riemann integrals, a standard theorem states that if Fn is a sequence of functions that converge uniformly to f on a compact set, B, then on non-compact intervals such as the real line, this is false. For example, take Fn, x, to be null 1 on, 0, n, and 0 elsewhere. For all n we have. The sequence converges uniformly to the 0 function, and clearly the integral of the 0 function is 0. Consequently, this demonstrates that for integrals on unbounded intervals, uniform convergence of a function is not strong enough to allow passing a limit through an integral sign. This makes the Riemann integral unworkable in applications, because there is no other general criterion for exchanging a limit and a Riemann integral, and without such a criterion it is difficult to approximate integrals by approximating their integrands. A better route is to abandon the Riemann integral for the Lebesgue integral. The definition of the Lebesgue integral is not obviously a generalization of the Riemann integral, but it is not hard to prove that every Riemann integrable function is Lebesgue integrable and that the values of the two integrals agree whenever they are both defined. Moreover, a function E defined on a bounded interval is Riemann integrable if and only if it is bounded and the set of points where f is discontinuous has Lebesgue measure 0. An integral which is in fact a direct generalization of the Riemann integral is the Henstocker-Euro-Kurzweil integral. Another way of generalizing the Riemann integral is to replace the factors xk plus 1aaxk in the definition of a Riemann sum by something else. Roughly speaking, this gives the interval of integration a different notion of length. This is the approach taken by the Riemann Stieltjes integral. See also, area, antiderivative, notes. References, Shilov, G.E., and Gurevich, B.L., 1978. Integral, Measure, and Derivative, A Unified Approach, Richard A. Silverman, trans. Dover Publications. ISBN 0-486-63519-8. Apostel, Tom, Mathematical Analysis, Addison Wesley, External Links, Haswinkel, Michiel, ed., Riemann Integral, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4a.